we left in the previous session, as we are in the photoelectric domain, as we realized when the energy of photon is greater than certain keV, it depends on the material to material. For example, this is a specific thing maybe for copper, but if you have a different material, then everything will be different because they depend on Z, all the cross sections. Okay, so this is done for a specific material. So there is no hard and fast rule that only that energy it will be there, but a particular material it will be some kind of a like defined. So what happens, we all know, we are very much familiar with the Compton effect. So you have a photon hitting an electron. Let's say this is photon hitting an electron. A photon goes out, and let's say this is my electron. So this is kind of scattered, and maybe this is my, let's say, original direction of photon. And these are the two angles. Let's say this is phi, this is theta. So when a photon hits an electron, the electron is the electron is moved, or like from this position it moves, and also the photon is scattered with certain angle theta. All of us are familiar with this Compton scattering, and we know that there will be a change in wavelength. So this is, let's say, delta lambda, which is equal to, let's say, the final lambda minus of initial lambda, which is equal to h over mc, or rather m0c if you like, and 1 minus of cos of theta. Okay, we are familiar with this formula. So this is what it happens in the photoelectric effect. The difference was the photon was absorbed and you see electron, but here the photon is not absorbed, the photon is scattered. You can see that photon is still there, and you have the electron which has come out. So that means whatever initial energy the photon used to have, this is now being shared between the scattered photon. You can say that gamma prime, just to make the notation correct. And then you have the electron, which is, so the total energy is being shared by photon and electron. Mostly the photon carries most of the energy. Depending upon the material, you can find out what will be the maximum energy. So this is the change in wavelength, which is represented by this formula, which is very much familiar to us. We'll look into this thing later on again, maybe in the afternoon class. We'll come back. Now the essential point that we see here, the photon energy, when it crosses certain energy, basically the photoelectric effect, because of the Z and other dependence that you have, energy dependence, energy to the power minus 7 by 2, sorry, minus 3.5. So the Compton effect actually dominates. Now here you can see that if you look at whatever reference frame we have started, let's say 1 keV or so, in the photoelectric effect it stops at some point, but this is the complete range of electron energy possible, right? So in the specific case that we discussed earlier, you have the nucleus, let's say like this, and then you have various cells, and if you want to knock out an electron with a photoelectric effect, then you need maximum energy to knock out from the K cell. Okay, if you want to knock out from L or M cell, the binding energy is a little bit less. So you need less energy photon to knock out an electron from L and M cell. But if you want to knock out an electron from K cell, obviously you need more energy. Now there the photon is absorbed and you get the electron. But here in the Compton effect, you have both of them. Now the photon actually, once it is actually, so this electron, when it is knocked out, again it will interact with the medium that we'll discuss later on, charge particle interaction with medium. Right now we are looking at the photon interaction. So that will see that it will interact with medium, and then we'll find out how it actually loses energy. But when it comes to photon, this photon is now free. So this photon is free, and it will be again, so when it will either, if it doesn't interact with anything, it will move edge like this, or if it retracts, then again it can does the photoelectric effect also. Now this energy, suppose this has certain energy, let's say 100 keV. Now this is energy is like shared between electron and this one. This has earlier it used to be a rest mass of energy of electron, but now it is moving. Some energy it has taken from the photon. So this photon energy is now reduced. So if the photon energy is reduced, then it is possible after some time, there is a possibility of again photoelectric effect. So again it will be having photoelectric effect, so that it will be absorbed, or it will just without interaction it will move on. Okay, so this is the basic difference between these two now. And another difference, striking difference, is that you have Compton effect almost every year, because if your energy is very much high, the Compton effect it needs any free electron, right? It could be L cell, M cell, or anywhere any electron it will find. Of course, depending upon the density of electron, it will be dependent the Compton effect, but it has nothing to do with any specific cell, let's say. Okay. The essential point is once it actually overcomes certain energy, then the Compton effect dominates. And as you can see, it will be like across energy from beginning to end roughly. But at a certain domain, it will be that it will be completely photoelectric effect, and maybe other effects are other kind of not that dominant. Let's see, the photoelectric effect is like going down. We'll see that there will be a new picture coming out soon, and then this picture will be changed. Okay, so before moving forward, let's see that there are a few possibilities when the photon interacts with the electron. It can have like the maximum time it actually follows this kind of pattern, or sometimes the photon, when it interacts, it goes very slightly deviated, and then the electron is also deviated, because the scattering angle is very, very small. But most of the time it have a reasonable scattering angle, so you can have a similar kind of picture. Or there is a possibility will be that it can also come back, hitting exactly head-on collision. There is a possibility, but very rare. Okay, so most of the time this what happens, and sometimes this also can happen. Now we have photoelectric effect, Compton effect, which is like the energy is shared, that I have already mentioned. So let's write down the scattering cross section for the Compton scattering, and it is similar to that one what we wrote earlier for the photoelectric effect. So what happens, as I said at the beginning, you have the Thomson scattering when the photon also interacts with electron. At the beginning, I think I mentioned, but whenever actually the energy of the photon is closer to or similar to the rest mass energy of electron, then the Compton effect, quantum mechanical effect dominates. So then Compton effect will be the most dominant part depending upon the energy of the photon. So the cross section sigma c, okay, this can be best represented this electron photon scattering by like quantum electrodynamics, what is called Klein-Nishina formula. Will not look into that cross section. I'll just write straight away. So the sigma c is c corresponds to Compton effect. This will be roughly like this, twice pi Re square. This is R, not gamma. This is Re square. Then you have lambda over lambda prime. I already defined there is some lambda and there is some lambda. Scattered one is lambda prime. This is square. Then you have lambda over lambda prime plus lambda prime over lambda. This is the scattering cross section. Okay, so here as you can see, you can notice that in the photoelectric effect, whatever we have done, we have actually taken Z into consideration because it was interacting with a medium. Okay, there used to be some atomic number associated with the medium, but here actually they are interacting with the free electrons. So the energy of photon is such that the electrons, they even if they are not exactly maybe k electron, but even k electron also can look to the photon almost kind of free, because the energy of the photon is very large. Okay, so that's what you don't have anything, all the memory of Re square. Re square, we have already seen the classical radius of electron, which already I wrote at some point. So that is there. Apart from that, you have the lambda and lambda prime, the initial wavelength and the final wavelength, and the scattering angle theta. So this is how the Klein-Lissner formula or the Compton scattering cross section looks like. Once you plotted energy versus energy, you can have this kind of picture. Okay. So this is how we converted the high energy photon, which is not available for photoelectric effect, but eventually it emits another electron and the photon energy is reduced. Further, there is a possibility of again absorption through the photoelectric mechanism. Okay. Now, so if you want, we can go to the next level. What happens? The energy is increased now further, because we started with low energy where the photoelectric effect was dominant. Then if you increase the energy, you go to certain domain, particularly let's say this domain to some other domain. Let's say this is completely the Compton effect dominated. But what happens if the energy of the photon or the initial photon energy becomes more than certain energy, so to say 1.02 MeV, then a new process takes over. Okay, so what is that process? We already watered that word in one of the, so this is 1.1 MeV, let's say. So this is at 1.02 MeV. Another process takes place. So what is this process? This is pair production. So when now you can see that if we vary the energy, then this domain, I can say, sorry, let me just put this domain. Correct. So during this domain, you can say that Compton effect is the dominant one. But so if the total I want to that calculate, then it will be roughly going like this. Okay, because this is the attenuation coefficient versus energy. You can see that. So what is so special about 1.02? Now we know that electron mass is 0.5 MeV, and so also if the particle has same whatever mass you have the particle from whatever relativistic Dirac theory that we have learned, that antiparticle will be exactly same mass. So if you combine electron and positron mass, it will be 1.02 MeV. So when photon in a particular medium, usually you cannot decay independently to a electron and positron pair, but as I mentioned at the beginning, you can have some kind of process. Let's say you have a positron. So I have written an arrow which is actually opposite. It says that it is an antiparticle, and then electron, maybe this is an electron, and then it, again a photon interaction. So this is a photon in some medium, let's say. So as you can see, the incident particle is photon, then it interacts with a medium. What you see is output is electron and positron pair, which is what is called the pair production. Now, as we say that when the energy actually crosses 1.02, it starts, but still Compton effect is dominant up to certain level. At some point, the energy increases few MeV, let's say, then pair production is the dominant one. It is not the Compton effect. So depending upon the energy domain, you have either photoelectric effect or Compton dominated or maybe pair production dominated. So whenever we look at the total the attenuation coefficient, it will be combination of all three of them. We'll see later on. Okay, so this is what the pair production is, and we can also find out the specific cross section. I'll write it right away and then see. There is one phenomena which actually happens, what is called a screening. I'll explain maybe after some time. So let's see how the pair production. So pair production, so the pair production cross section for is something like, again you see that Z appears here because it has to be in certain medium. It cannot be just electron. Okay. So that's what the medium comes into picture. So Z, the atomic number of that medium is Beck. Now you have alpha. Alpha characterizes that it is electromagnetic interaction. Then you have Re square. Again, there will be some complicated formula, so let's not worry too much about that. So 7 by 9 log of 2h nu divided by me square. Then you have some function of z, and then another numerical value 109 by 54. Anyway, these are like they will have certain contribution, but mostly you can see the dependence here. It's again, it is a z dependent function is there, and energy of the beam is also involved. Now z alpha, which is a constant, and Re that we already learned in the earlier cases, basically the classical electron radius. So you have this kind of domain, but nevertheless we need to also remember that there is something called some factor, which I'll without explaining a note here, there is something called screening effect xi, which is involved in this formula basically. If z it is there, so I have not written explicitly, it is something like 100 me c square h nu, so E plus E minus z to the power 1/3. So what happens? Now you have a material, you have a specific medium. So let's say you, let me give a very simple example. Let's say you have a nucleus which consists of protons and neutrons, and then let's say what is this will be usually a positive charge, right? It cannot be, you have either proton or neutron. So obviously it will be positively charged. If it is positively charged, it will be surrounded by electrons. Okay. So now if another photon comes in, then although photon is neutral, but it has to have, so the nucleus is kind of screened. It is not kind of sitting idle. Okay. So this is a screening factor. This is more relevant in the Bremsstrahlung case than here, but more or less same thing, because that will be more prominent in the Bremsstrahlung case. That will be the charge particle. And here also you have the screening effect, which will be actually the nucleus is being screened by this charge cloud electron. Okay. So we will not go into that one, but as we learned that this higher energy domain will be actually kind of completely dominated by the pair production after the Compton effect. Okay. So let's come back. So this is the rough graph of we have for the various processes, Compton, pair production, and the photoelectric effect. This can also be shown in a different diagram, something like this. Maybe another one. So this will be atomic number of the observer and versus the photon energy in MeV. Okay, so let's say this is 60 MeV, and so what will happen? Let's say 0.1. This is, let's say 100. This is 120, and so on. So this will be some domain. This one. So this domain is completely dominated by photoelectric effect. Middle is always Compton effect. Then the last one is basically pair production. So this is the line which actually separates photoelectric from Compton, and this is the line roughly depends. It's a specific material we have taken an example. This also separates from Compton to the pair production. Now we can see that for almost all the energy you have this specific case which is dominated by Compton effect, as I said earlier. But if you are in very low energy, then it's a photoelectric effect, and if you go to high energy, it will be the other one. Okay. So let's come back to one example that I told at the beginning, was the radiation collision. we'll learn more about this thing later. So maybe I can postpone it because it is related to the charge interaction, but let me just mention it right away. So you have an electron, actually goes as an electron, and then goes as an electron, emit a photon, so an electron actually goes as electron, but still there will be, the electron actually emits as electron, but in the process it actually emits a photon. Let me redraw the picture again. If you remember, we had some kind of a nucleus. As you can see that instead of photon, now my electron is the beam. So whenever it comes very close to the nucleus, let's say, there will be electromagnetic, or there will be Coulomb effect between electron and the charged nucleus, and because of that there will be some additional energy, it will be picked up, and that will be radiated as some kind of photon, which is called Bremsstrahlung photon. Process. Okay, so this will be more or less similar to the pair production that we mentioned, but this will be more the classic difference is earlier you had the photon was the beam or source, photon was the beam, but here you will be the charged particle or any charged particle it will be, but we will see that the Bremsstrahlung will be more dominated for only E plus and E minus rather than other charged particle like proton or alpha or any other particle. Okay, so why is it so? So if I write the cross section, maybe it will be important. So let's see what the cross section says. So if I write the similar way that I wrote the cross section for pair production, if I write the sigma for the Bremsstrahlung, it will be something like 4 Z square Re square alpha, again d nu over nu. Then we have some formula phi of phi 1 of xi. Again, xi is some screening effect that I wrote in case of the pair production. Similar kind of effect will be here, minus 1/3 log z minus of fz. This is a function of z, already we know. Then minus 2/3 epsilon and phi 2 z, xi. This is the function of the screening by 4 minus 1/3 log z minus of fz. Anyway, this is, we don't worry too much about this factor. There will be some effect because of screening and the z effects are there. But look at the part which is like multiplied to this bracketed function. You have z square, again you have r square and alpha, which characterizes that it is an electromagnetic interaction. If you look at this formula, r square, it has e square over 4 pi epsilon me c square. Okay, sorry. Okay, so this is r square. Is it correct, or did I make it wrong? Can you, anybody can check r square? That is r, not r square. Okay, fine. So the definition of r is like this, but r square will be m square. So now if you have an electron, as you can see, the mass of the electron is 0.51 MeV. And so for the proton is also the same. Now let's say you want to have, instead of electron, you have a charged particle like proton. Proton also will move, and maybe there will be some kind of a Coulomb interaction between nucleus and repulsion, let's say. There is a possibility, but as you can see, the effect will be dominated for electron and positron, because here it will be the mass of the electron will be the dominant factor. There will be a huge enhancement only for electron and positron, but for higher mass particle, the Bremsstrahlung effect will be not that relevant. So that's what you have for electron and positron, it will be very much dominant, and for other charged particle, although there will be some effect, but it will not that much dominate. So that's what, whenever we talk of any beam of electron and positron, we have to look into, if the energy is very high, we have to worry about the Bremsstrahlung radiation. Okay, so we'll see more about this, but before I move, let me just plot the cross section. So this is so in the same graph you can see that if is the energy of the electron, after it is like this is 500 keV. So at some point the Bremsstrahlung contribution will actually start. Similar to the pair production, there will be also Bremsstrahlung effect, but it is not that much dominant than the other effect that I already told. That's what, this was not the main process that we wanted to discuss. The main process were photoelectric effect, Compton effect, and also the pair production. So these are some of the processes that will be looked into when you look at the photon interaction with matter. So now let's look at other aspect. We'll move soon to the charged particle, so to say heavy charged particle. But before we move forward, let's say you have the range of the particle, basically charged particles. So okay, maybe I'll come back after some time. Let's see. So the range of charged particle. Okay, so let me give the principle. So whenever you have a medium, any kind of medium, and you have a beam which is a charged particle, heavy charged particle. Let's go back to our particle. Go back to our definition when I introduce the particle content. You have the heavy particle which are like proton. Of course, neutron is neutral, so we'll not look into that. You can also have alpha, you can also have pion, etc., but pion effect will be limited. But mostly, let's say you have a proton or alpha, which will be very much similar. And you can also have light charged particle. Light charged particle, which is basically your electron and positron, let's say, dominant. Okay, so there will be two kinds of effect for the charged particle interaction with medium. One will be the heavy charged particle, and the other one will be the light charged particle. So let's say you have charged particle which interacts with medium, then what will happen? It will lose its energy. Interacting with medium will discuss after some time, but we can find out what is called the minus d over dx, or the energy which is lost when it passes certain distance dx. So minus d, let me write down the formula. I will come back to this formula again later on. So anybody who knows what is the name of this formula? Bethe-Bloch equation. Very good. So let's see what it says. So the Bethe-Bloch equation, let me just write straight away. I'll explain this to some extent later. So let's say you have minus d over dx equal to some constant, let's say 4 pi any electron numbers density, again Re square MEC square, the density of the matter Z over A, small z square over beta square, beta equal to V over C. Then you have log of twice ME, let's say. I'll not explain this thing right now, but we'll come back later on to this. W max divided by, let's say, I square minus of 2 beta square. I didn't use so far the correction factors, but let's not worry too much. So when a charged particle passes through a medium, it will lose energy. This is roughly the Bethe-Bloch equation. There will be some corrections added here, but we can find out how much energy it is going to lose. So from that we can find out what is the stopping power, but I will discuss later on. Okay. So let's go back to where we are there earlier. We wanted to discuss something else, basically charged particle, right? So what was that? The range of the particle. So what was the range? So we have, when the charged particle moves in a medium, almost it is rectilinear, and it continuously and slowly deposits energy, and finally it is, let's say, it stopped at some distance. Okay. And but if it is electron, let's say, if it is electron, then the electron can have like a very like zigzag path, and finally at some point it will be stopped, let's say. Okay. So this is heavy charged particle, and this is light charged particle. Okay, so this will be like the average, roughly the average distance that heavy charged particle will be, because it will be almost rectilinear. But this will have like, say, the energy will be less, and it's a light mass particle, so there will be some different rates. So from that point of view, what will happen whenever the charged particle will be there, as I mentioned, it will almost will be equal to the average distance. That is what is called CSDA, continuous slow down approximation. Continuous slowing down. And this is defined something like this, or CSDA. Is 0 to Ek0. This is the initial kinetic energy. dE over AC, which is a function of energy, or AC total. This is nothing but d over dx that I wrote, the stopping power, which will come back to that. So the moment I know the stopping power, we can actually start from 0 to, you integrate this d over AC from 0 to the energy of the particle that you start with, what you get is RCST. Okay. So you can also find out something called R50, R80, like up to 80% what is when it actually transfers, and the total energy is dissipated up to 50%, 80%, and so on. So for various ranges are they are in use. You can look into some attenuation. Suppose you have a monoenergetic, let's say, beam, particularly a photon, and it is, let's say, it hits some kind of target, let's say. So when it interacts with the target, whatever is left out, let's say, you can write dn equal to minus mu, and it, suppose the thickness is dx, let's say, so mu dx and n. Okay, that means we can write from this one, this is the first order differential equation. So you have nx equal to n0 e raised to the power mu x, where your mu is the attenuation coefficient, okay, which actually we plotted in the photoelectric effect, Compton effect, and pair protection. You have seen in the left hand side, we used to have attenuation coefficient. Now this attenuation coefficient mu actually is a combination of all three processes. So you can write total mu equal to the contribution coming from photoelectric effect, contribution coming from Compton effect, and also the contribution coming from the pair production. So this is We'll see a little example later on, but for the time being, so depending upon the energy, we know that there will be relevant contributions from photoelectric effect, Compton effect, and pair production. So all of the components will be added up to find out the total attenuation coefficient of this one. Okay. There is also called mass attenuation coefficient, which is nothing but you just divide by the density, then you have mu and divided by the density, what is equal the mass attenuation coefficient. And this is actually unit is cm square by gram. Okay, so we'll discuss a little bit more later on in the next class. We'll come back to this, but this is very much trivial thing, nothing special. We might use it at some point. Let's look at some another process, what is called the electron capture. Suppose you have, let me erase a complete one now. Don't need this one. You have some Z, some specific element with Z. It actually captures one electron and goes to Z minus 1. Some Z converts to Z minus 1 with a emission of a positron plus a neutrino, so to say, called a beta plus process. I'll come to beta decay later on in the next class. So it is possible that one of the protons number is reduced with the emission of a positron and a corresponding neutrino. Or there will be something like that. You can also have an electron coming to this side. So electron is actually absorbed. So Z plus E minus going to Z minus 1 plus. So these are the two competing processes. In one of them, this is what is called your electron capture. So one of them is beta plus emission and the other one is E capture. But if you look at in the right hand side, you have a positron here in addition to a neutrino, but here you don't have neutrino. The difference is if you do not have, so this has minimum energy, let's say 0.511. So if the available energy is not that much in this process, particularly we don't know what kind of specific Z we are considering. If the available energy which is emitted is not more than, let's say, 0.511, this process will not take place. So obviously this will, the alternate process will be this one, but unfortunately we may not be able to easily find out what has happened, because it is very difficult to identify whether the neutrino is produced, because it is a neutral particle and it does not interact with any material, hardly it interacts. So that's what, but we can actually identify from the energy changes basically in the certain level. So from this we can find out whether it is a electron capture or a beta plus process. We'll learn a little bit more about the beta minus process later on, but they are competing with each other. So the emission energy will be more than 0.51 MeV, then there is a possibility of beta plus emission, or otherwise it will be just a electron capture. So what happens, suppose you consider, let's say you have a nucleus, something like this, and let's say the electron orbit will be like this. Now pictorially you can write that, say, electron is certain, maybe this is K cell, let's say the immediate cell is K cell and the electron is here. So electron actually is absorbed by the nucleus. What exactly you get is particularly it goes to a different kind of nucleus with Z minus 1 with the emission of a neutrino. Okay, so this is one, or you can also have the competing process will be like it goes to an electron or maybe a electron type sorry, neutrino. Okay. So the effect will be same. If you remember, the atomic radius will be roughly of the order of angstrom, whereas the nuclear radius will be of the order of Fermi. So it is a bit rare process that electron will be captured by the nucleus, but nevertheless we have seen processes that we can have electron capture. This is one of the processes that we have, and the emission of gamma rays takes place whenever there will be additional energy. Okay, so one process in which you have gamma emission is whenever a cobalt-60 decays with, so gamma emission can take place basically whenever there will be some charge particle, let's say alpha, most likely it is beta, then it will be accompanied by some kind of gamma radiation. For example, let's say you have cobalt-60, so which has 5 plus angular momentum, let's say it decays by beta minus, which goes to a state with 4 plus, and the half-life is 5.3 years. So this is in an excited state, and there will be like it should come back to the ground state, which is the nickel-60 with emission of 2 from photons. So let's say they are instantaneous, because so 1 photon will be emitted, it will go to, so this one is basically, let's say this energy is, let's say 2823.63 keV. The intermediate state is 2158.80 keV. With the emission of photon, it comes to another state 1332.50 keV, which is 2 plus state, and then finally with another photon it comes to the nickel-60. So these are the 2 photon emissions. So sometimes there will be alpha emission, but mostly it is the beta which is accompanied by the gamma rays. So this is the basic difference of gamma and X-ray. As you notice that the X-rays are actually emitted whenever you have the atomic transition, basically whenever there is a vacancy in certain atomic levels. Basically we already learned in the beginning that there will be X-rays, but the gamma rays actually comes from the nuclear. The origin is different here, although you cannot like the energy could be same for photon and X-rays, but here it is likely that the energy will be much more higher, and it is more kind of a danger, because we know that it's more like it can penetrate very far distances. So one of the possible examples where you can see the alpha emission is the radium 88 going to radon 86 plus alpha particle with emission of 4.6 MeV energy. Okay, so this kind of, we are not going to discuss anything about the alpha emission, but this is one such process where you can have the alpha and beta, sorry, alpha, beta and gamma radiations. Okay, so let's quickly start and then go over something else. So as I said, we learned a little bit about the interactions of photon with medium. Now let's look at the possible effects of the charge particle, which I already wrote the formula. Let me erase this portion also, because this will not really help. When you have charged particle like protons and alpha particle. As I classified, you will have heavy charged particle and light charged particles. Proton, alpha, etc., and electron and positron. Okay, let's come back to the formula that I wrote. From there, we'll start explaining. So minus, I'll explain a little bit more about the formula later on in the next class. Minus d over dx equal to 4 pi Ne Re square C square rho Z over A Z square over beta square log 2 Me square. Okay, so whenever a charged particle, so to say heavy charged particle, we are starting with the heavy charged particle, we will come back to the light charged particle later on. So there will be energy loss in the medium in which, suppose the particle is approaching a medium which has atomic number Z, and you have the charged particle which has small z basically, depending upon what kind of charged particle you are considering. And beta is, what is beta equal to V over C. You have electron mass here. We learnt Re, the classical electron radius. Then electron density, you have the density of the medium and atomic number of the medium. And this is the maximum energy basically that can be released in one collision. Okay, so maximum, this is what is called the maximum energy transfer in a single collision. And there is another one which is relevant, I, which is equal to mean excitation potential. Okay, so there is a beta square here. I'll just explain the salient feature here, then we'll come back later on and we'll stop after that. So if you plot d over dx versus, let's say, beta gamma, there are 4 processes. Have something like this. So this is not the graph that I drawn at the beginning, but something different. Now what you can see is that maybe this region can be identified as A, this one is the B, then C, logarithmic rise is there. I'll have some corrections here which I did add delta correction and C, the cell correction, I'll add later on, and then D. Now, if you look at the A factor basically, where you can see that there will be 1 over beta square decrease. So the first part is like rapidly decreasing with beta, roughly with the energy of like velocity component is here, 1 over beta square. Whenever it comes to point B, which is called minimum energy, let's say ionization point, after some time there will be a relativistic rise, the logarithmic factor will take over, it will come to this point, and then finally there will be a region which will be kind of more of a plateau, and this will be very, very high energy will go. Okay, so these are the 4 factors that you have. Now when you look at here, most of the, for a specific we have similar kind of charged particle, they will have more or less the similar kind of minimum ionization points, but this point will be more or less similar with little bit of difference we will see on specific cases later on. In this point where this is very low, you can have different particles which will have different kind of identifications. For example, let me give one, let's say for proton. Similarly, maybe there will be something that will be different. Let's say for pion. So there will be some difference here, not exactly same, but there will be difference. So we can actually identify below the minimum ionization point for various particles, but after all it will be a little bit different. And you can see that later on, once we add the correction factors of cell energy and the density factor, so there will be some kind of correction here, and the point will be kind of reduced. We'll see a little bit more about this in the next class. So I think I will stop here. Before we stop, we have the stopping power that I already used in one of the formulas in RCSDA basically, while using the range of the particles. So this is basically S equal to minus d over dx that we already used, what is called the stopping power. We will discuss a little bit more as we progress. Okay, so I think I'll stop here. You can close it.